How do you mine a rock worth $10 quadrillion when it has no gravity to hold you down and is moving 10 times faster than a bullet? This is the central engineering paradox of the next century. We have identified objects in our solar system, like the asteroid 16 Psyche, that contain enough gold, iron, and nickel to collapse the global commodity markets on Earth. But between us and that wealth stands a wall of pure physics. In the vacuum of space, the traditional concepts of landing, standing, and drilling do not exist.
On Earth, gravity is our greatest ally, providing the friction necessary for every machine we have ever built. In the asteroid belt, gravity is a whisper, a force so weak that a single sneeze could launch a rover into a permanent orbit. To harvest the riches of the heavens, we must first master the art of staying put. This is not a story of science fiction, but a breakdown of the extreme space engineering and orbital mechanics required to tether ourselves to a mountain traveling at 40,000 miles per hour.
To understand the scale of the challenge, we have to look at the target. Most people imagine an asteroid as a stationary rock floating in a dark void. In reality, these objects are kinetic monsters. They are traveling at orbital velocities that dwarf anything we experience on Earth. When we talk about mining an asteroid, we are talking about a rendezvous between two objects moving at hypersonic speeds. But speed in space is relative. The real problem isn't the velocity, it is the lack of mass. Earth has a mass of 6 sextillion tons, creating a gravitational pull that anchors everything to its surface. An asteroid like Psyche or Ryugu has so little mass that its escape velocity is measured in centimeters per second rather than kilometers per second. If you were to stand on a small asteroid and jump, you wouldn't land. You would become a human satellite, drifting away forever. For a mining rig, this means that every action has an equal and opposite reaction that is potentially catastrophic. If a drill applies 100 pounds of downward force to the rock applies 100 pounds of upward force to the drill. Without gravity to hold the machine down, the drill doesn't go into the rock. The machine simply pushes itself away into the abyss.
This brings us to the first major hurdle in space engineering for mining, the anchoring system. We cannot rely on weight, so we must rely on mechanical or physical bonding. In the early days of asteroid exploration, mission architects proposed harpoons. The concept seems simple. As the spacecraft approaches the surface, it fires a high-velocity projectile tethered to a cable. The harpoon penetrates the surface, expands its barbs, and pulls the craft snug against the rock. This was the strategy for the Rosetta mission's Philae lander on Comet 67P. However, space rarely rewards simplicity. When Philae attempted to anchor, the harpoons failed to fire, and the lander bounced. It didn't just bounce once, it drifted for hours in the low gravity, eventually landing in a dark crevice where its solar panels were useless. This failure taught the aerospace community a vital lesson. The surface of an asteroid is an unknown variable. It could be solid metal, or it could be a rubble pile, a loose collection of dust and rocks held together by almost nothing. A harpoon hitting a rubble pile is like shooting an arrow into a bag of flour. It won't hold. If harpoons are too risky, we have to look at more advanced methods of attachment. This is where electrostatic grippers come into play. This technology utilizes the same principle that makes a balloon stick to your hair. By creating a significant potential difference between the gripper and the asteroid surface, we can generate an attractive force. In the vacuum of space, this electrostatic adhesion is surprisingly powerful. NASA and various private aerospace firms are currently developing pads covered in electrodes that can induce a charge on the surface of the asteroid. This works regardless of whether the surface is made of conductive metal or insulating silicate rock. The beauty of electrostatic gripping is that it is non-destructive and adjustable. If the sensor detects a shift in the surface material, the system can modulate the voltage to maintain a constant grip. However, there is a catch. Asteroids are already electrically charged environments. They are constantly bombarded by the solar wind, which strips electrons from the surface. An engineering team must ensure that their gripper doesn't create a massive electrical arc that fries the spacecraft's delicate avionics. Beyond electrostatics, we have the mechanical solution of microspines. Inspired by the way insects and geckos climb vertical walls, microspine technology uses thousands of tiny, independent hooks. Each hook is designed to find a microscopic irregularity in the rock surface. When 1,000 of these hooks engage simultaneously, they create a redundant and incredibly strong bond. This is particularly useful for the $10 quadrillion rock scenarios because many high-value asteroids are thought to be M-type or metallic. A metallic surface might be too hard for a harpoon to penetrate, but perfect for microspines to latch onto. The engineering required to make these spines work in the extreme temperature fluctuations of space is staggering. The metal must remain flexible at 200 degrees below zero and rigid enough to hold a multi-ton mining module when the sun hits it and temperatures soar. Let's talk about the actual process of mining once we are anchored. We have established that Newton's third law is our enemy. If we want to extract material, we need to apply force. Traditional terrestrial mining uses heavy machinery that uses its own weight to create leverage. In space engineering, we have to rethink the drill itself. One solution being tested is the counter-rotating drill. By having two drill bits spinning in opposite directions, the torque forces cancel each other out. This prevents the spacecraft from spinning like a top the moment the drill hits the surface. But even with zero net torque, you still have the longitudinal force pushing the craft away. This is where the anchor must bear the entire load. Every gram of material excavated must be balanced by the structural integrity of the anchoring system. If the anchor fails during the drilling process, the recoil could snap the tether and send the mining hardware tumbling into a non-recoverable trajectory. This leads us to the concept of orbital mechanics in the context of mining. You aren't just anchoring to a rock, you are becoming part of that rock's mass. As you extract ore and move it into a containment vessel, the center of gravity of the entire system shifts. If the asteroid is small, the act of mining can actually change its rotation or its orbital path. Future tech solutions involve using the asteroid's own material as propellant. Imagine a mining rig that takes the waste rock, or regolith, grinds it into a fine powder, and uses an electromagnetic railgun to shoot it away at high speeds. This would act as a massive thruster, allowing the engineers to stabilize the asteroid or even move it into a more convenient orbit around the Moon or Earth. This is the ultimate goal of asteroid mining, not just taking the minerals, but turning the asteroid itself into a navigable spacecraft.
However, we cannot ignore the rubble pile problem. Recent missions like OSIRIS-REx and Hayabusa 2 have revealed that many asteroids are not solid rocks at all. They are more like cosmic beanbags. When OSIRIS-REx touched the surface of the asteroid Bennu, the surface acted like a liquid. The spacecraft's arms sank 19 inches into the rock with almost zero resistance. If you try to anchor a traditional mining rig to a rubble pile, the anchors will simply pull the rocks out of the pile rather than holding the craft down. For these types of targets, the engineering shifts from anchoring to enveloping. One proposed concept involves a giant high-strength mesh bag that completely surrounds the asteroid. Instead of anchoring to one spot, the bag distributes the load across the entire diameter of the object. Once the asteroid is bagged, the mining rig can operate inside the net, using the tension of the mesh as its reactionary force.
There is also the challenge of the tumble. Very few asteroids rotate on a clean, predictable axis. Most of them undergo what is called complex rotation, or tumbling. This is caused by the Yorp effect, where sunlight hits the irregular surface of the asteroid and creates a tiny amount of thermal torque. Over millions of years, this can make an asteroid spin faster and faster or tumble uncontrollably. Anchoring to a tumbling object is like trying to jump onto a moving carousel that is also being tossed around on a stormy sea. To solve this, aerospace engineers are looking at de-spinning missions. Before the mining rig arrives, a fleet of small tug spacecraft would attach to the asteroid's poles and use high-efficiency ion thrusters to slow the rotation down to a manageable rate. This is a massive undertaking that requires precise synchronization and years of constant thrust, but it is a necessary precursor to any large-scale resource extraction.
Let's dive deeper into the chemistry and material science of the tethers. When we talk about anchoring, the cable connecting the craft to the anchor point is the single point of failure. In the vacuum of space, materials behave differently. Metals can undergo cold welding, where two clean metal surfaces spontaneously fuse together upon contact. If your tether mechanism cold welds in the wrong position, the mission is over. We have to use advanced polymers and composites that can withstand the intense UV radiation of the sun without becoming brittle.
Carbon nanotubes and graphene-reinforced fibers are the leading candidates for these tethers. They provide the highest tensile strength-to-weight ratio known to man, allowing for a cable that is thin enough to be stored on a reel, but strong enough to hold a mining station against the centrifugal forces of a spinning asteroid. The economic incentive for solving these engineering hurdles is unparalleled. The asteroid 16 Psyche is approximately 226 kilometers in diameter and is almost entirely made of metal. On Earth, we have to dig through miles of silicate crust to find small veins of metal. On Psyche, the metal is the crust. The iron and nickel alone are valued at $10 quadrillion, but it is the rare earth elements and platinum group metals that are the real prize. These are the materials required for every high-tech device, every electric vehicle battery, and every solar panel on Earth. Currently, we are stripping our own planet of these resources at an unsustainable rate. By moving the heavy industry of mining into the asteroid belt, we don't just get rich, we move the most environmentally damaging parts of our economy off-planet. But how do we get the material back? This is the final piece of the anchoring puzzle. Once you have successfully anchored, drilled, and processed the ore, you have to launch it back to Earth. You can't just throw it. You have to navigate the complex gravity wells of the inner solar system. The most efficient way to do this is through gravity assists and ballistic capture. By timing the launch from the asteroid perfectly, the ore canisters can use the gravity of Mars or the Moon to slow down and enter Earth's orbit. The anchoring system plays a role here too. It must act as a launch pad, holding the remaining mass of the asteroid steady while the ore is accelerated away. This requires a level of structural engineering that we have only recently begun to simulate with supercomputers. We are currently in the Sputnik era of space mining. The missions we are seeing today, like the Psyche mission launched recently, are scouts. They are mapping the gravity fields, measuring the surface composition, and testing the very anchoring technologies we have discussed. The results from these missions will dictate the design of the first generation of commercial mining rigs. We are moving away from the era of flags and footprints and into the era of infrastructure and industry. The transition from a terrestrial civilization to a spacefaring one depends entirely on our ability to interact with these moving rocks. It is not enough to just reach them, we must be able to work on them. The complexity of this task cannot be overstated. Consider the thermal environment. An anchored mining rig will have one side facing the sun, heating up to hundreds of degrees, while the other side faces the absolute zero of deep space. This creates massive thermal gradients that can warp the frame of the machine and snap the anchors. The engineering solution involves active thermal management systems, using liquid metal coolants to move heat from the sunlit side to the dark side, maintaining a uniform temperature. This is the kind of high-level aerospace engineering that Not Magic is all about. There are no simple answers, only elegant solutions to incredibly difficult problems of physics. As we look toward the year 2030 and beyond, the roadmap for asteroid mining becomes clearer. Phase 1 is the identification and characterization of near-Earth asteroids. Phase 2 is the deployment of small-scale prospector drones that will test various anchoring methods, from harpoons to electrostatics. Phase 3 is the establishment of the first permanent anchoring stations, which will serve as fuel depots. By extracting water ice from asteroids and breaking it down into hydrogen and oxygen, we can create gas stations in space. This solves the rocket equation by allowing us to refuel our ships without having to haul all that fuel up from Earth's deep gravity well. Once the fuel is secured, the transition to metal extraction begins. This is where the $10 quadrillion valuation comes into play. The sheer volume of material available in the asteroid belt is enough to support a human population of trillions, but it all starts with that first successful anchor. It starts with a machine that can reach out, grab a rock moving at 40,000 miles per hour, and refuse to let go. The technology being developed today at JPL, ESA, and private startups is the foundation of a new era of human history. We are no longer limited by what we can find in the dirt of our home planet. To the skeptics who say it is too hard or too expensive, history offers a different perspective. Every major leap in human capability was once considered an engineering impossibility. Crossing the oceans, powered flight, and landing on the moon were all impossible until the right combination of physics and persistence was applied. Asteroid mining is the next logical step. The physics is understood, the engineering is being refined. We know where the rocks are, we know what they are made of, and we are learning how to hold on to them. The first person to successfully anchor a commercial rig to a high-value asteroid will likely become the world's first trillionaire. But the real benefit will be for all of humanity as we unlock the infinite resources of the solar system.
This is the reality of our future in space. It is a future built on the back of rigorous engineering, precise calculations, and a deep respect for the laws of motion. There is no magic involved in capturing a $10 quadrillion rock. There is only the steady application of force, the clever use of electricity, and the unyielding strength of a well-placed anchor. As we continue to push the boundaries of what is possible in aerospace, the asteroids transition from distant points of light to the fuel and steel of our future civilization. The void is not empty, it is a treasure chest, and we have finally figured out how to build the key.
In the end, the challenge of anchoring to an asteroid reminds us of our place in the universe. We are a species of builders and explorers, standing on a slightly larger rock, looking out at a sea of smaller ones. Our ability to bridge the gap between these worlds is the ultimate test of our ingenuity. Every harpoon fired, every electrostatic pad activated, and every microspine engaged is a testament to our drive to understand and master the environment around us. The $10 quadrillion rock is waiting. It is moving fast, it has no gravity, and it is indifferent to our presence. But we are coming for it, and we are bringing our anchors. We have covered the physics of the void, the mechanical hurdles of low gravity, and the cutting-edge technology designed to solve these problems. From the failures of early landers to the promise of biomimetic grippers, the journey to the asteroids is a masterclass in space engineering. As we move closer to a resource-rich future, remember that every step we take into the cosmos is governed by the same uncompromising laws of physics. Mining the heavens is a daunting task, but for the engineers of today and tomorrow, it is simply the next problem to be solved. This is not magic. This is the future of human industry.